I'm going to start sharing my screen now. All right, there we go. Are you looking at my slides?
Yes.
Great. Okay, and now you should be looking at them in full screen, right?
Yes.
Okay, so I'm going to talk a bit about the machine learning models that we're currently using in the ALeRCE broker. So we have been doing, within the group, we do a lot of machine learning research, okay? But what I'm going to show today is the machine learning models that are in production. And this, these two models, we have two models. I'm spoiling you. I'm spoiler alert, okay? But we have basically two models. One is what we call the stamp classifier, and the other one is the light curve classifier, and I want to talk a bit about them. So first thing that I want to convince you is that machine learning in astronomy has had a huge impact in the field, right? So what I'm showing here in this plot on the x-axis is the year, and on the y-axis is the number of papers obtained from the world of science in the field of astronomy and astrophysics that has the words machine learning in it. And you can see that maybe 10 years ago, we didn't have many papers in machine learning in astronomy, right? But I would say after 2014, they started growing. And last year, 2019, we had a huge number of papers in that are related to machine learning in astronomy. This year we have less, but of course these years have not ended yet. Now this is tied in with what deep learning is. So maybe some of you have heard about this. I'm going to talk briefly about this in the next couple of minutes. But deep learning is like the new machine learning. It's a subfield of machine learning, and that has had a huge impact in the world, in many things. In our phones, for example, a lot of deep learning is going on there. The first papers in machine learning, in deep learning for astronomy were published in 2015. And since then we started growing, and in 2019 we had a huge number of papers that had deep learning applied to astronomy and astrophysics. Okay, so this is just to convince you that machine learning is important in astronomy. Okay, so the question is, what is machine learning? So machine learning, you can think about it as the study of algorithms that improve their performance at some task with experience. So a well-defined learning task has to have these three components: the performance, the task, and the experience. Okay, and it has to, and this algorithm has to learn from the experience on some particular task. So how does this work in general? So we have our machine here in the center, and what we do in practice is we just feed it with data, right? So we teach him through data. So we get a lot of data, and we teach the robot how to learn a specific task, and at some point it's going to learn it, right? And then we can ask him or it a question, and the robot is going to return us an answer, right? And hopefully it's going to return us the right answer, and it's going to return us the answer that he's going to learn from the data. So an example, a very simple example is, imagine I want to classify animals, right? And on the x-axis here, I'm showing the animal size, and on the y-axis, I'm showing the ear size of the animal. And I can get a dog that's pretty large and with big ears, okay? But I can also have a small dog with big ears, okay? And I can start filling this in with dogs, and then I can have a big dog with small ears, and I can fill this up with a lot of dogs. And then I can say, okay, well I want to classify between dogs and cats. So I'm going to get some cats, and I get a cat, a small cat with big ears, and then I have a huge cat with small ears, and I start filling this in with cats, right? And what you may have noticed here is that I can separate between dogs and cats just by drawing a line, right? So this is the basics of what the machine learning algorithms do. They try to get the parameter space and split in terms of classification, try to predict which class it is by splitting the space somehow. Okay. So An example of this is what a decision tree is. And let's say I want to classify here between triangles and circles. And I can say, okay, I'm going to split X1 in this case by a line, right? And by doing that, I'm going to have two subgroups. One, the one on the left has 1 triangle and 6 circles. The one on the right has 8 triangles and 2 circles. And I can continue doing this, right? And now I can split on the X2 coordinate, and I'll have 2 sub boxes, right? And I can continue doing this and so on and so forth. So this is what a decision tree is, right? And so decision trees are not really amazing or anything like that, but what's amazing about them is that you can combine them by using what we call the random forest. So the random forest is basically you train randomly these decision trees, and by having M of these random decision trees, N decision trees, you can have a classifier that is really, really good, is amazingly good, okay? Now, I told you about deep learning, right? So what is deep learning? Deep learning is another kind of models that try to emulate mathematically what a neuron does, like a biological neuron does. So instead of using a neuron, what we do is model the neuron mathematically, right? And now, in the case of a biological system, what we can do is we can have like a nervous system by connecting lots of these neurons, right? The same thing you can do by connecting artificial neurons, and you have this artificial neural networks, okay, that are very famous, very popular nowadays. And the whole thing about this is finding a way, a smart way of connecting these neurons, okay? So this has had a huge impact in many fields, not only astronomy, okay? So most of the state-of-the-art machine learning methods nowadays are related to finding new ways of connecting neurons, right? Now, the traditional machine learning approach, what you do is you have the data. So let's say you have this image. And what I do is I, the human, try to calculate features out of the data. So I create features out of the data. So I say, okay, I'm gonna see if it has doors, or if it has, I don't know, tails, or if it's hairy or not. So I build filters to do this kind of stuff. And once I have all those features, I throw them to a model that it can be a classification model, and then it outputs, it is a car or it is not a car. The change of paradigm is that on deep learning, you don't need the human, right? So you don't need to define the features for the data, right? The feature extraction is done directly by the neural network. So that means that you can stop relying on humans a bit, okay? So on ALeRCE, we have in production 2 main models. The first one is what we call the light curve based classifier. And this is a paper that has been recently submitted by Paula. And it's already on the archive. So if you want to, you can go and check it out. And what we did is that we grabbed the light curves and we classified them. So the light curves on ALeRCE, right, from CDF. And this is the taxonomy we defined. So you can see that we have transient, stochastic sources, and periodic, and each of them has subclasses, right? And what we do to classify into these subclasses is we start by getting the light curve and calculating features out of the light curves. So we have features such as features related to magnitudes, features related to periods, features related to autocorrelation models and stuff like that. So we have a whole bunch of features that we calculate on the light curves, and then we put these features into a random forest. Now, why a random forest? Well, the reason is that it is the model that had the best performance in terms of the classification that we want to achieve. Okay, so when you connect to ALeRCE and you use the light curve based classifier, what's behind that classification, it's a random forest. Okay, but what we also did is at some point we asked ourselves, okay, but I want to find, so Pancho asked this. I want to find a supernovae on real time, like at the moment of exploding, right? So what we did was Rodrigo with Esteban developed a convolutional neural network that's able to grab the images, such as the template, the science, and the difference images, and throw them through one of our convolutional neural network models and predict whether this is a transient, an AGN, a variable star, an asteroid, or something else such as a bogus alert, okay? Notice here that we also use the metadata that's coming in from the alert stream, okay? And now the way we check if these models are okay or not is we use stuff such as the confusion matrix. So for example, here we have the true label of the object, and on the x-axis we have the predicted label. And you can see that, for example, we find 90% of the AGNs, 94% of the supernova, and 90% of the variable stars, and 96% of the asteroids, and 97% of the bogus that appear on the data. So just think about this. This is with just one alert. At the moment, we receive one alert with no other history from the source. But at the same time, as I told you before, we have the light curve based classifier, and this has a more fine taxonomy. And here we're able to classify between all these sources that I talked about before. Okay, but the other thing we did is we compared both of them. So we say, okay, if our stamp classifier is saying this is a supernova, does that mean that the light curve classifier is going to say it's a supernova? And in practice, the answer is yes. We find this. Okay, so that's good. So as a summary, so the first thing that I want to convince you, and I hope I did in 1 minute, is that there has been a major success of machine learning applied to astronomy. And this is during the last, I would say, 2 or 3 years, this has been majorly done by applying deep learning methods to astronomy. ALeRCE strongly relies on machine learning models. So we have these 2 models in production, but we also have a lot of other models. We have the light curve classifier and we have the stamp classifier, and you can access the predictions of those classifiers directly from our database. And the thing is that as I told you, we're developing a whole bunch of models. Some of them we have them more developed than others, but putting them into production takes some time, but more models are coming. Thank you.
Thank you, Guillermo. I think we have a couple of questions. So the first one is, in regard to the hierarchical structure, what happens when you get something that is not there, but is of physical interest? Do you account for that in any way?
So I think that Paula can respond better to this than I, but we have other kind of objects here. Now, if you're thinking about something that we don't have on our training set, then this classifier is not going to work. But we're also working on algorithms for outlier detection to try to find those anomalies. Paula, do you want to say something about it?
Yes, with the current model, what happens is that if the real label is not present in the model, the classifier assigns any label, the most closest label to the target. For the case of periodic, we have the periodic others class, but for the case of stochastic and transients, the model just assigns the closest class.
Do we have time for a second question?
Yes, one more question, I think.
Okay, so Cristobal asked, could one incorporate on the fly correlations between light curves of nearby sources? And he's thinking about time delays in strongly lensed sources.
I don't know about, I mean, in principle, you can, right? Now, the thing is, how hard is it to do that? Do you have an answer for this, Paula?
Currently, we don't have any model in production that can measure time delays, but the statistics group, particularly Felipe Lorrieta, is developing a method that might be able to detect that, but it's still in development.
I can also comment that I think the strong lensing group in the LSST is interested in this kind of question, and there are also a few groups, but this requires a very special database design because you're combining time and space. It's the most difficult kind of query. So perhaps we should end here.
Yeah,
and
there are lots of
answering-
questions in the chat. I just realized,
Yes.
but I think we can answer them live on the chat, right? So I can
Yes.
start.
Yes.
So we will leave the Zoom open, and we will come back in at 2:45. Sorry, sorry, at 3 p.m. Sorry, in 15 more minutes.
So maybe I can stay here and answer some questions, right? If someone wants to.
Yeah, maybe.
Well,
Leave if they want. So Guille, do you want to start doing that?
Yeah, I'm trying to
Maybe
figure out where in the chat is
someone
he
have
asking.
maybe if someone have questions, they can raise their hand because maybe you are answering questions and the person is not here.
Oh yeah, that's a good point.
Maybe what one is get
Yeah, but,
why the stamp classifier was deep learning. Maybe
there's a
Guille,
hand.
you can.
Wait, can you say that again, Paula? I heard it
Almendra
sounded like if
say,
you were underwater.
oh, sorry. Almendra said that she didn't get why the stamp classifier can be considered as a deep learning algorithm.
Oh yeah, I can show you that. So we have a whole bunch here of, so this is a neural network, okay? And we have a whole bunch of convolutional layers here in this part. So deep learning is basically grabbing neurons and do a deep architecture in which you have different layers, one after the other one, neural network layers, right? So usually you say that if it's more than maybe 3 or 5 layers, then it's deep learning. If not, it's like classical neural networks. But it's also related to the kind of architectures you're using. So in our case, we're using convolutional layers. Here we have a whole bunch of them. And then those go into dense layers. So that's why it's called deep learning. And that's why our model is a deep learning model.
There is one raised hand. Gustavo?
He just write in the chat. He was
Okay.
asking about how will the SpaceX satellites affect the LSST as a whole and the classification of the sources by ALeRCE.
That's a very good question.
That's a very good question. I don't have an answer for it. I think Ignacio may have an answer for this, right?
For the
About
SpaceX?
Yeah.
No, but it's a very important problem, and the question about how that will affect, especially for the long exposure images, it's not clear. And how do you diminish the reflectivity of the satellites that are already in space? I think that is it's a combination of a scientific way to handle the problem, but also a political question about how do we take measures to diminish the problem in the future.
Alex Racim is asking, what was the data set used for training and testing the classification model? So we did a lot of cross-matching. Yeah, so a huge part of this project was doing cross-matching.
Yeah, there are several catalogs available, particularly for the case of AGNs. He's asking particularly for that. We used the MIDI-Quas catalog, but also some external SDSS catalogs. And we use both CTF bands, GNR, the public bands. So that all the results that Guille was showing are for the combination of both bands. So we have features that are measured in one band in particular, and also we have multi-band features. Yes, someone also asked how we deal with the imbalance issue. And I think Ignacio answered that. Yes, we use the ALeRCE package. That is very good. I recommend you to use it if you have highly imbalanced data
Yes,
sets.
as I remember, well, we use a random forest in the imbalance learning package, which is basically an extension of scikit-learn. And as I remember, they do oversampling on each of the trees, on each of the decision trees, but it's not done in a typical way, in the sense that first you repeat the samples from the classes that you have very few of them, but instead they do it in a per tree basis. So like I think they split first data into, or they sample first the data for each tree, and then they repeat the objects from the underrepresented classes.
Ignacio?
Yes.
So I want to encourage people to have a little rest, because the next session is going to be a bit intense for some people. So I think it's better if people go and have a break, a little break, and we will be back at in a few minutes. But of course, you can keep asking questions by the chat.
All right. I think we answered most of the questions now, right? I think we answered all of them.
Yes.
Yep. Anyway, if you have more questions, you can ask us directly through email or something like that.
Okay,